Let's see. So the quiz was okay. I guess two groups got, let's see, I think two groups did poorly on it, and then everyone else did okay. I think it was like mostly 88, seemed like what everyone got on the quiz. People seem to have trouble with the let's see, that's okay. Quiz 14. People had trouble when they put it into the Excel to minimize it. Mostly people got this. I mean, they got the reaction constants. Everyone got the reaction constants, and then a couple of people had errors in like the negative signs here that they got the wrong. Anyway, what I did was, so instead, there were kind of like two options for grading. I could have taken 12.5 off for each, or I could take 2 points off for every number, and that was a more gracious way. So I took the 2 point off thing. So that helped a lot. And then, because some of these, like you would get all these, right? I mean, these are the initial conditions. So anyway, so mostly people got the first part pretty well. They didn't get this number though. I think only 3 groups or something got the actual reaction coordinate. So the minimization, it was a little tricky because of this reaction has these huge numbers in it. So it's powers to the 21, and you have to, in order to get that to minimize, you have to divide this thing by a big number. I think it said to divide it by 1e to the 50, but you could have divided it by something even larger to get it to minimize, because the value you get, it'll go positive and negative, just a small, like 99.595 will be like negative, and 99.59, it'll be negative to the 10 to the 20 or 30 or 50. And if you go change that 6 to 7, it'll be positive to the 50. So dividing it by 1e to the 50 kind of helps that. I think you could also have taken a log, like a log ratio of the answers and log of that. That could probably be a route to get it to work. Let's see if I think I have the Excel open. Quiz 14 K-Calc. That's a K-Calc part. So that was kind of straightforward, I guess. Just put in the stoichiometry. And then this part, that's just the answer sheet. And then where's the other part of it? K-Calc thermal part G. Answers. Yeah, that's the calculations. So I minimized this. Let's see. Oops. That's not what I wanted. So I just divided by 1e to the 50. Like if you change this to like 0.9958. So that would be 21 minus 21 times 10 to the 50, because I divide by it. So see, that's some huge number, just a small change. And then if I make it 0.9960, then it's 30 times 10 to the 50. Let's see, they're both negative. One of those should be positive. 60. It's negative. That one's positive. So see, that would be, that's already like I don't even know. It's times 10 to the 50. So it's like 10 to the 70 or some huge number, right? So that's why dividing by 10 to the 50 gets you the answer. We'll minimize it. So anyway, so even here, it's e to the minus 7, then times 50. So that's e to the plus 43. It's still not 0, right? So you have to divide that number, the target, by some big number to get it to go even close to 0. The minimization is going to a fixed value here, in other words. So it's not a ratio of the values. So it's kind of an odd. The solver routine's a little bit got some nuances to it. Anyway, so let's get back to that. So most people got that. They couldn't get this minimization to work. So anyway, that only was like 2 points, so it didn't really matter. The range thing, though, so this part everyone got the range because it's kind of simple. You have this is like if the reaction coordinate's 1, then that's 0. You can't go below 0, so that thing has to be less than 1. And then this thing is the reaction coordinate, so it has to be bigger than 0, right? And the others all follow suit. They'd all be within that range. The second one, though, with 2 reactions is a lot more complicated, right? And again, it's like kind of trial and error to get the answers. No one, I think anyone even came close, so that was kind of disappointing. But and there was an old quiz where the answer to this was given, so something similar to this. So anyway, I guess people, for whatever reason, but I think there was the high grade was something like 92, and then a bunch of people got 88. So it didn't seem to matter that much. 2 groups, I think, got in the 60s, but they messed up even the first part. So, I'm not sure what happened. This one, there were a lot of because it's pretty tedious to do this, to get this right. So there were a lot of minor errors in here, like plus and minus signs mostly. So anyway, there is only a couple points though here and there. And then this one, so then you can just get these to be bigger than 0, right? So this from C10H22, you have this guy has to be bigger than 0, right? Because that if that's 0, it's less than 0, you get negative. And then from the total sum, which I think is the strictest, is the least strict restriction, then you get this 13 by 2. Like if this, if you set these 2 equal, then this reaction coordinate has to be 130 divided by 20, right? And it can't be bigger than that because that would make this sum negative, and you can't remove that. That can't be negative, right? So anyway, so that's where I get the 13 by 2 from that restriction. If you plug that in to all these, it also works, right? So it's less of a restriction than any of the other ones. So that means that's a good one. And then once you have this range for the first reaction coordinate, then you have to plug it in here. So from the CO one, you have these things have to be by a factor of 10, right? So 10 times this second reaction coordinate has to be bigger than 10 times E1, or else this thing doesn't work. In other words, you get a negative amount of CO, which can't happen. I mean, you can't create CO, right? Then the other one comes from, and the same thing applies to H2, right? It's also a factor of 10. And then, let's see, the H2 is the other one. That's this one. So if you set E2 equals 21 reaction coordinate 1 minus 30, then you can solve that and find that you have 30 minus 21 reaction coordinate 1 for the maximum value. You could have this. If it's larger than that, because it's negative here, you get a negative H2. Right, so the second one depends on the first one. So they aren't independent. Right, so you have to have equations for these. It isn't just a value. And that's similar to the previous quiz. There's a previous quiz like that. So there was an example to kind of go after. So I'm not sure, no one got that. I think nobody got either of these. So I'm not sure why. And then anyway, that wasn't that important. These equations were the important part. And I think one group got these answers right. So again, like when you minimize this, you have to, for the first reaction, so for the two coordinates, for the first reaction, you have to divide by e to the 58 for this, or it won't work. Because you have to get these two numbers to be about in the same range. And about e to the -7 for the solver to work. So that's kind of it. And then as far as this thing goes, so you're producing, so your goal in this thing is to produce this decane, right, from hydrogen. So how much conversion to decane are you getting? So basically you're not getting that much, you're getting like 15% conversion. Whereas if you run the reaction alone with CO, which costs money, then basically you got 100% conversion. Right. So so for that reaction, if this is 1, that's 100% conversion. So people were getting like 5 for that, and they were saying it wasn't enough conversion. So that didn't make any sense, you know. So basically you have to kind of sort out what these conversions mean in terms of the reaction. But 15% doesn't seem like very good. But the CO2 is free, and the CO costs money. So basically, this would seem to be viable if you put in more CO2 probably, or increase the pressure or something. Let's see, the pressure is even on the first. On the second, pressure will help drive it. So you could pressurize it more. That should increase the conversion. There's probably some other things you could say. I mean, except that anything that kind of made sense here. If you said something that didn't make sense, I took 2 points off. So that was kind of the grading on that. Any questions on the quiz? So anyway, two people, the grades are like 89 or something. So I said they didn't need to take the final. And everyone else, it seems like it would benefit you to take the final. The final is going to be on electrolytes, so probably something kind of simple for the first question, and then the second question will be like something from the course overall, you know. And I guess on Wednesday I'll go through kind of what could be on the final. There's no previous homeworks for this section, you know, on electrolytes. I just kind of brought that up now. This will be used in this flood diagram thing, which is it's a plot. So it's a Cillian diagram. It's called like 4 different names. Basically, it's pH versus concentration of the ions, and use that to do some calculations. And then there's answers here for the homeworks, and then the test yourself is pretty simple, so it doesn't have answers. It's just run the osmotic pressure equations and other things. And the equations are given, so that shouldn't be too bad. So anyway, that's the story. And then so the timing is that what I looked up is that the finals on our time slot is Monday, 12 to 2 p.m. So I thought I'd give you the problems at least Friday. And you'd have weekend to do it, and turn it in sometime on Monday, maybe before midnight on Monday or something like that. And then that should be okay. Let's see, wait a minute. No. The schedule is for Thursday at 12 to 2. So, okay, so this is just like our normal exam time almost. So I'll give you, we'll just do this similar, except you can turn it in later. Like it doesn't have to come in on Saturday. Maybe you need another day, like Sunday, to get it turned in. And then let's see. I'm not sure when the grades needs to be in, but you have like a 2-day buffer at the end to do this pass fail thing. So that's the only reason to turn it in sooner, like to get the exam turned in sooner. I haven't figured out the logistics on that. Like the last day, like when you have to make your decision, that's kind of the issue. Because I don't mind to give you more time on it if you want, but I think we should, if you can figure out when you want to, how late you want, I'll get you the quiz, the final by Thursday at whatever, 12. And then you guys can figure out when you want it turned in, because then I'll get the grade back to you probably 2 days after you turn it in. And then so it has to be within the window when you can decide what you want to do with the pass fail thing. Right. So I don't really care when you turn it back in, put it that way. So, but basically it has to be within that timing. So, and I haven't figured out the logistics of that. But nominally, let's say I'll give it to you on Thursday and then turn it in on Sunday night at midnight. That's probably good enough time. If not, if it isn't enough time, let me know. Like we can negotiate it or whatever. So anyway, any questions on that for the final and stuff? So it'll be 2 questions similar to what you've had. And then one will be on this electrolytes and the other one will be probably on one of the quizzes that people did poorly on, maybe at the beginning. Yeah, because people have doing pretty well, like later on. So with the group thing. So it was kind of halfway through that we did that switch. So anyway, hopefully that'll work out. I wanted to do this electrolyte thing because I noticed, like in doing plant tours and things, that a lot of people are working with sulfuric acid and everyone uses caustic and stuff. So the thermodynamics of those systems are different than everything else we've been covering and different than the reaction equilibria. So it's got its own than reaction thermal. So it's got its own nomenclature and stuff. So basically it'd be good to see. I'm not sure if you get this in the other classes. So I thought that he has a chapter on it. It looks kind of important, but it turns out the chapter is at least half biology, which I don't think you need, right? So it's a little hard to dissect the biology part from the chemical industry part. I'm trying to focus on chemical industry in here. Part of the biology part, though, has to do with bioengineering, like bioprocess engineering for fermentation, which is people are working on, right? So I threw some more books up here, which this hasn't updated, I think. Let's see, reaction engineering I put up. This book, right, Electrolytes, is a pretty good book. That's like the book that's cited in a lot of different places, but it's, for one place, it's cited on the, if you look up electrolytes or Debye theory for electrolytes, they use that book as a reference. It doesn't look to me like it's a very good book, actually. It's really wordy and just goes on and on. You might like it. It's got a lot of sketches. It's not full sentences type thing. It's kind of funny. It's almost like notes. There's another book on electrolytes. Pitzer is a guy, I think he's a guy, we looked at Pitzer earlier, right? So he's the guy that made those Pitzer charts with the compressibility factor. Anyway, he's the head of chemistry at Berkeley. He's dead now, but he founded that department, and then he became like really famous. So he also, I guess, specialized in electrolytes, and he wrote a book on it. And this is his book. So that's a pretty good book, actually, when you look through it, but it's really long. I think it's got 22 chapters, and all of them are dense. So that would seem to be a go-to book, but it's old too. It's from this, I'm not sure, like 80s, I guess. So you might want to look at that. I mean, if you want to look, there's some books, and I also put in, which isn't here now, but I put in a book on biological chemical engineering, like fermentation stuff, which I think that one might be worth taking a look at. I think there's some course that Go is a guy in environmental that teaches on that field. Anyway, a lot of departments, chemical engineering departments, teach a course in bio fermentation stuff. So you kind of glance through that book, it'll probably give you just about as much information. I'll put it up there. It's not up there yet. Anyway, so there's a lot of different aspects, and then electrolytes are also going to cover like chlorination of water. So if you work with the water treatment plant, or all the salt treatments like flocculation, all that stuff is electrolytes. So there's a lot of different areas, wastewater treatment, and then probably that's freshwater treatment before it goes in the feed, and the wastewater treatment is another area where it's going to be like electrolytes. So there's a variety of areas where you wouldn't expect. And if you work in surfactants, it's all electrolytes. So soap, like Procter and Gamble. So it would seem like electrolytes is the main area. The chapter, like a lot of his chapters are really complicated, and they don't seem to get to the point exactly. But anyway, it's a framework at least to work with. Since I'm not an expert on electrolytes, it's someplace to start. But these other books could help. I didn't actually find anything that really was like that appealing to me as like a simple description of electrolytes for industrial use, for chemical industry. So anyway, the thing with electrolytes is they speciate, which means that they break up into different things. So you have a variety of different chemical equilibria going on. So like this is sulfuric acid, right? So there's 100% sulfuric acid over here, this side, then this is 0%, and it's in water. Like almost everything is in water. It doesn't have to be. There's things called ionic fluids that are waterless electrolyte systems, right? And those are getting to be more and more common. It's something that seemed to become popular about 15 years ago, and then now it's a solvent that you can use. It's something like water, but it isn't water. So if you have reactions you're running that are sensitive to water, you can do it and they need to be speciated like this, and you can do it in an ionic fluid, right? For instance, I mean, a lot of these are high temperature, like molten sodium chloride would be an ionic fluid, right? And then we talk, let's see, we can talk about it, but basically when they do this concentrated solar, so they have a field of mirrors and they shine it on a spot, and the temperature gets to 4,000 degrees. So they need a heat transfer fluid. So they use an ionic fluid. So you use something like a salt, like sodium chloride, and then it melts, right? And they make a molten sodium chloride that runs through insulated pipes down to a heat exchanger, that it makes steam, and then they make electricity with the steam from that. The nice thing there is you can take the molten salt, put it in an insulated tank, and store it hot, and then when you need to make steam, tap it out. So it's a way to store electricity. Using that setup, they can continue producing electricity for something like 5 days. Even if it gets cloudy out and it rains for 5 days, your power plant can still run. So it's kind of, molten salts can be like a battery. It's kind of a battery for heat. Anyway, so this, like you only get the H2SO4 population. This is the amount of the species when it's going to 100%. And then there's other ions are formed, like SO4 2 minus, and there'd be H plus, 2 H pluses produced from that, right? So in between, so as you increase the concentration, you get different speciation, right? And this also, so you can add in something like NaOH to this, and then that would shift the speciation also. So it's going to be that you have your electrolyte, which is sulfuric acid here, is the sulfate ions and protons. And then you can add in a salt to buffer it to reach a certain pH where the thing will have the species that you want present. So you might be running reactions and one of these species is better than the other. Right? So that's kind of the idea. The speciation issue is the main issue. So you can see there's a prediction of the speciation, like there's a model that's been fit to the data and those data points, right? And the coarse grain features are captured by the model, right? So that's kind of the idea. Like if you're working with sulfuric acid, what exactly are you really working with? Is it H2SO4, right? Which has no protons, right? So it's not acidic, right? So when you get pure H2SO4, that isn't releasing any H pluses, so it's not an acidic material. Whereas when it's dilute, you have a lot of speciation into sulfate, which has 2 H pluses going into the solution, so it's really acidic. Right, so your acidity is going to change as you change the concentration. So it's important. And you can see it's not a linear function of the concentration; it's some weird function with things hopping all over the place. Right, so basically, to understand kind of what's, or just not necessarily to understand, but to be able to predict what's going to happen for an industrial process, you need to kind of have some special understanding. It's not a normal chemical reaction. There'll be a reaction constant for the dissociation, right, and the speciation, but basically it won't be, it's not going to be some kind of linear function, right? So in this topic of electrolytes, so you put salt onto ice to melt it. So we looked before, these equations we've seen already, like melting point depression we saw already. I forget what chapter it was. So these are all what you call colligative properties. So if you have your solvent, let's see, not that. This guy still running is good. So if you have a solution and then you're putting in some particles of some type, right? And say you have a membrane here. So you have water, then you have water over here, and then you have something in it. So that something could be Cl minus Na plus, right? Or it could be any number of things. So usually ions, so electrolytes. So you're going to treat those as if it's like a gas. So if you forget about the water and just say these things are floating around, each one has kT energy, then they're going to act like a gas. Then you're going to have like pi is going to be 1 over the specific volume times RT, like PV. Right? But here 1 over V is the concentration. Right, so that's called the osmotic pressure. It means that the water wants to dilute the material over here so it wants to drive in through here. The ions can't pass through the membrane, so the pressure here goes up, and the delta P is this pi. In other words, if I put a tap here, this one would be higher than that one, because the water wants to flow in to dilute. And basically, you can talk about that pressure difference as the pressure of these things flying around like a gas. Right, so that's this osmotic pressure. So here it's instead of the concentration, you talk about the activity. Right, and then this log thing, this would normally just be like this. The log thing comes from his chapter or whatever where we went through this. The normal way to deal with this is to say you have this concentration dependence and do a power series in concentration. Like this would be the second virial coefficient for osmotic pressure, B2, which has to do with the kind of the interactions between the ions in here. So anyway, so you can also get it with this ln of the activity, which is kind of like the Gibbs free energy of this thing. So anyway, that's kind of how this equation is what we're using in this chapter. Again, like this is the normal way to do it. This is how he does it. This is the way we're using it because all the problems and everything we use this equation. This is the normal for melting point depression. So you can see the activity is something that you want to know in all of these. that's the thing that's going to affect these colligative properties. This is boiling point elevation, so it's kind of the same. It's the same kind of equation. So basically, these are all colligative properties, counting how many of the things are in there. So the practice problem 1 is just use these equations on some system. It gives you the numbers and plug them into that. So that part should be kind of familiar to you. We've already done this freezing point depression business, right? Put sodium chloride, ethylene glycol or glucose to melt the ice. And then which one works better? Just plug into this melting point depression equation. Put in the concentration and then get the temperature T out if you know the heat of fusion, which is given here, I think. Anyway, this is 6009. Someplace it's given. Or you just look it up in the back, I guess in the back of the book somewhere. The heat of fusion is given in the table, the first table in the appendix. Anyway, I'm not going to go through that. Basically, that's just plug and chug of that equation. There's nothing special about it. Osmotic pressure is the same thing. It's just basically plug into that equation. Again, this isn't really exactly the normal equation, but basically it's the one he uses. So say for water, if it's 100% water or almost 100%, then you say that the activity is 1. So basically, or the activity coefficient is 1. You just put the mole fraction water in here. And that's the usual assumption. So, because you're usually working with a dilute electrolyte. So that business, and then the boiling point is the same thing. It's just plug into that equation, get the shift in the boiling point. All right, so you can write a reaction for water, right? So water dissociation. So water will dissociate into protons and hydroxyls, right? And then this constant, it's like an activity constant. Since this is liquid, the activity is 1, so that isn't used in this equation. So it's just going to be the proton concentration times the hydroxyl concentration. And this activity coefficient is 10 to the 14. Right? So if these are equal, then each of these is 10 to the minus 7. Right? And then this pH. So pH is minus log base 10 of the H plus. So you can have POH also. And that's going to be minus log 10 of OH minus. Right? So in this case, if this is 10 to the minus 7, this thing's 7. So pH of 7 is that you have the same amount of the two components, right? And you can log of the activity coefficient is minus of the Gibbs energy by RT. So you can get the Gibbs energy. So one thing to do is you can get the Gibbs energy from the back of the book. So we can calculate the Gibbs formation energy, or the change in Gibbs formation energy for the components on the two sides. Those are all given in like this chapter. So you have the Gibbs energy for formation, and then numbers given in the table. Right? So whatever. So you have the Gibbs energies of the components. So you can calculate them, take the log base 10, and then get natural log, and then get the activity, get the equilibrium constant from that. Right, so that's the same thing we did in the chemistry, in the chemical reaction chapter 17. This is some, let's see, what is this? This is just experimental data for sodium chloride. Right, so moles or mole fraction of sodium chloride. Oh, this is just showing that there's two ways to write about this. You can do like mole fractions. You can do weight percent, so mass per volume. And then you can do mole fraction, so moles per total moles. Then you can do this molality, which is moles per weight, like moles per kilogram. Right, so the electrolytes, they use molality, right? So it's like, and then these are the densities of the solution, right? And molarity, so molarity is moles per liter, and molality is moles, molarity is moles per liter, molality is moles per kilogram, I think, right? So the concentration is gram per liter. Let's see. This is the first time I've done this chapter, so it's kind of like not that smooth, but we did pH, molality, and molarity. Anyway, there's the two sets of units. He goes through a whole, I thought I had written this down here, but oh, here, AH is moles per liter, molarity, neutral solution, temperature. What's molality? Molality, number of moles per kilogram. That's what I said, right? So basically, molality and molarity, the difference is going to be with the density. That's why the density is given here. So the density of the solution changes with temperature. That means that the molarity, so as the solution gets a higher volume, as you heat it up, the volume increases. That means the molarity will like change with temperature. That's the point of this, sorry. So as you change the temp, so you got to look at an electrolyte solution and then change the temperature. The density changes. That means the molarity, which is related to the mole fraction, so it's moles per liter, changes because the volume gets larger. So it drops, right? But the molality doesn't because it's moles per kilogram per weight. So the weight doesn't change with temperature unless it evaporates. Basically, the molality won't change, right? And neither will the mole fraction. So molality is a better number to use if you're looking at temperature changes, because the molarity changes with temperature. When you get to low concentrations, the molality and the molarity are the same value, almost the same value. But as you get to higher concentration, they're different values. Right, so you can see, so basically, usually we're working with low concentrations, you can interchange molality and molarity. But if you get to high concentrations, you can't. Right? And so that's kind of the point, that the units of this whole system get to be messed up. In the back of the chapter, he's got appendices that go through all the different units that people use for electrolytes. So there's some confusion over that, and he's trying to be helpful by putting that in. All right, so let's see. So anyway, there's going to be some Ka for dissociation. I call it Ka. So it's a dissociation constant, right? So it's basically the same thing as a reaction constant. So you use the dissociation as if it's a reaction. So you start with acetic acid, and then there's going to be water involved in the reaction. So it's like an acid base, and then you make a proton, which will actually be H3O plus. That's written H plus. So species is actually going to be H3O plus, and then you're going to have the base, which is the negative component here. Right. So the speciation involves this constant. It's minus 4.8. So that means that this is going to be probable that this will happen because it's bigger than 1. The 4.8 is bigger than 1. That means it's likely it's going to drive over here. Right. So this happens when you put it in water. When you put acetic acid in water, it'll speciate. right? So again, this speciation constant is temperature dependent, just like the reaction rate constant that we had was temperature dependent. So this is called a monoprotic acid because it's just got one proton to give, right? But if you have like sulfuric acid, it's got 4 protons to give. That means it can speciate 4 times. So you get 4 different things out of it, right? So basically, this is the simplest case is a monoprotic acid. So there's what they call an apparent concentration, which is what you put in. So you weigh in a certain amount. And then the actual concentration of acetic acid is going to be different from that because it's speciated into this conjugate base. Right. So the actual concentration is going to depend on this equilibrium constant, the Ka. So pKa is going to be similar to pH. It's going to be on the same scale. Right. So we're going to make a plot where you can find pKa on the same plot as pH. Then you can construct kind of what's going on here. And the other thing is that say this acid species, you know the vapor pressure of the acid in equilibrium with the solution, or you know the vapor pressure of water in equilibrium with the solution, right? So if you can measure the vapor pressure of water, that's going to be equilibrated only with the liquid form or only with this unspeciated form. So this ions can't equilibrate. They can't go to vaporize because they're coupled. There has to be a charge balance here. So you have to have equal plus minus. If this guy evaporated, you'd have a problem. Like you'd be creating a arc or something, like there'd be electrical non-neutrality. So you'd have a charged liquid. So that doesn't happen. So basically, because you have to have these two, this guy can't evaporate, that guy can't evaporate, but these two can evaporate because they don't have a charge on them. Right. So basically, these things will be in equilibrium with a liquid and solid form. If it's going to precipitate out a solution, it's got to go from the ion over to this, and this thing can precipitate out. Or if it's going to make a vapor, it's got to go from the ion to this and then go make a vapor. So this Ka, so you can be driving the speciation to the left if you're evaporating the components, right? And the Ka is going to govern the rate of that, and that'll govern kind of what's going on in terms of evaporation. So you can have speciation and vapor liquid equilibrium going on at the same time. So yeah, maybe. So this, like when you get pH, it's a mole. So that's kilograms per, that's moles per kilogram, right? It's not molar. In other words, moles per volume. Right? So and then this is just showing how you do this, the pH, and then the POH as Ka, how these are all related to each other. So pH plus POH equals pKa water, which is 10 to the minus 14. So if the pH is 6, then this has to be 8. Right? So if they sum to 14. If pH is 1, this has to be 13. POH has to be 13. Right, so that means that on this just shows, like for this acid, right, so this can dissociate twice. It's diprotic. So it's got, on each end, it's got a proton that it can leave. So that it can have this Ka1 and Ka2. It's got 2 Ka reactions, right? And then the balance between the solid and the vapor occurs with this aqueous form, and then the speciations happen separately. So if you have this, if you want to talk about the C plus balance with the solid, you have to go through these other Ks. So K speciation is going to be KSLE times Ka1 times Ka2. So that the equilibrium constants multiply. So you have to go, in order to get from there to there, you have to go through the root, through that, and then that. You can't just go directly. So you have to reprotonate it and then reprotonate it, and then you can precipitate. Right, so that's kind of how these things work. So it's a liquid. The equilibrium is between the liquid species, the aqueous species, and the vapor and the solid. So let's see. So this is what happens when water actually dissociates. So it isn't really splitting into protons and hydroxyls, right? It's actually splitting into hydronium, this H3O plus, and hydroxyls. It's kind of more convenient to talk about it in terms of H plus at times. So when you write the reaction, so there's a lot of these reactions in the back of the book, say, these dissociation reactions. There's a table. Let's see. Constants. Dissociation constants, right? So this is table. Dissociation constants, carbon dioxide, hydrogen sulfide, oxalic acid, this is succinic, and this is a bunch of these pKa1, pKa2. These are all polyprotic acids. And monoprotic was here too somewhere. I mean, they have it for biological molecules, but so I guess they don't have monoprotic in there. It's all diprotic. Anyway, so this so this is just showing that how that works. So if you have multiple reactions, you multiply the reaction constants to get the total reaction. That's kind of the idea of this. But all right, so this is the monoprotic ones. This is, I guess, just in the chapter. So the monoprotic things are just here. The diprotic are at the back of the book. Or if it's diprotic, it's the first reaction. So you go to hydrogen disulfide with hydrogen sulfide to this ion. Right, so anyway, actually the other one's here too. So HS minus is here somewhere. HS minus is here to S2 minus. Okay, so it's got two boxes here. There's a box up here and there's a box down here. So why are those boxes there? Well, if you're in an aqueous environment and you're more acidic, so your pKa is larger than let's see, hydronium. So this is 14 for the dissociation of water to H3O plus. And then H2O is also 14, right? H2O to OH, right? So dissociate H2O to OH minus is 14. Dissociate hydronium to water is 14, right? This is the base pKa base. This is the acid pKa, right? So if you're working in water, you have something that's more active than water. Its pKa will be governed by the water one. So basically, the water one, the most acidic you can get is this hydronium to water. You can't get more acidic than that, but you can still report the pKa's for these. The things in that category that are stronger than the dissociation of water are called strong acids, right? So these are all strong acids, meaning they have a larger pKa than water. And then the same thing at this end, like bisulfite, ammonia, and hydroxide ion dissociation will, and this is going from OH minus to O2 2 minus 2, are called strong bases. Right. So basically, things in between, if you're near the middle, it's called a weak acid or weak base. Right. So most of the things of interest are kind of weak. The things of industrial scope are going to be like H2SO4 and sodium hydroxide, which is here. So I guess it's just the hydroxide reaction with the bottom one. So strong acid, strong base. Or NaOH, right? Is that here? I guess NaOH isn't here. That's kind of weird. Anyway, NaOH would be a strong base. Right, so I don't see it here. So anyway, this is a list of the kind of ranges. And then, so if they talk about a strong acid, basically it's going to be based on the water dissociation. If talk about a strong base, it's going to be based on this, the water dissociation to the hydroxyl. This is hydronium speciation to water, whatever that is. So those are the cutoffs for strong acid and strong base. The pKa's, if they're in between the values, then that's like a weak, in the middle, they're a weak acid, weak base. So you talk about weak acid, strong acid. It's based on what if the dissociation's larger than 14 for the two, right? So that's the point of that. This is the Cillian diagram. I mean, just showing it, teach how you use this thing. So basically, if you have, so the strongest acid you can get would be the hydroxyl, would be the hydronium dissociation to water, and the strongest base would be hydroxyl to O minus 2. So those two would be like limiting. So if you have, this has to cross, so the concentration of protons is going to be 10 to the minus 2, right? If the pH is 2, so the numbers would be the same. And then it's going to go down until you reach 7, which is where the hydroxyls and the protons match to make 14 when you multiply the two. And the strongest base is going to be 14. It's going to go down to 7. So basically, there's a straight line for acid H plus or H3O plus, and then OH minus. It's going to be a straight line on this. And then the remainder, like if you're at 10, then you're going to have 4 to make 14, right? Or if you're at 7, they're both 7. So the two numbers add up in terms of pH. They add up into 14. And then this is the concentration of the two. So you'd have 10 to the minus 4, 10 to the minus 4 H plus ions, and 10 to the minus 4, 10 to the minus 4 the OH also at the same. Since they have to be charge balanced, so the plus and minus have to match. So they have to be the same on both sides, and they have to follow these two lines. If you have weaker acids and bases, they're going to follow these other lines, right? As they dissociate. So that up here would be the pKa of the acid or the base. The pKb would be here, and the pKa would be over here. Then there's a straight line of slope 1 that goes down. Okay, to cross the center line of this thing. So this is just drawing the lines for all different acids and bases. Okay, so this is kind of the beginning of this, looking at this Cillian diagram. Anyway, so I'll go through more of this next time. So we'll see how far we can get through the chapter. We'll definitely be able to construct these Cillian diagrams, do an analysis of dissociation, which will probably be on the quiz. So we're out of time. So, all right. So thanks. I'll see you next time. Is there any questions? Anything? Oh, so that time.